Hi friends, welcome to the new video of this lecture series. This is the lecture 4 of timing analysis and discussions. In this lecture, I try to cover one of the most important constant which is a setup constant and what is its mathematical expression. So before going to deep into this topic, in the last three lectures, we saw how the timing things work and what are the timing definition related to the basic timing analysis. Based on that, I think in the last lecture, I discussed about the static timing analysis and dynamic timing analysis. Both two are the timing constraint, and that timing constraint have some timing parameter constraint, which is a very important two of the very important timing constraint. One is a setup constraint and one is a hold constraint. In this video, we try to understand what is a setup constraint suggest. So here you can see I taken again one same sequential uh, two flop which is synchronously clock connected, and there is a combinational circuit in between that. By this circuit representation, we try to understand how the setup time. So let's mention this is a flip flop 0, which is a launch flip flop, and this is flip flop 1, which is a capture flip flop. So the setup things, there is a two basic definition I try to explain, and by that I think you will understand. The very basic definition of the setup time is, which I can suggest, that forget about the launch and capture flip flop everything. Just think that there is a flop. Consider this is one of the flop. This flop, there is data input is coming, D2 pin. Suppose D2 pin, so data is coming one by one. So and you have to sample the data at the particular clock edge. Either it can be negative or positive clock edge. So suppose you want to sample the data with proper one uh, positive edge of the clock. So whatever the data is coming, to properly sample at the particular edge, the data should be stable before some time of that particular clock edge, and before that minimum amount of time it's taken to sample that data at the particular clock edge, that minimum amount of time we can say it is a setup time. This is a very simple one. I can also explain this with a timing diagram or with a timing graph. Suppose this is one of the clock diagram you can see. Suppose there is one data is coming from the Q1 pin, and the data is almost like, there is a data coming from the Q1 pin, and data is almost like this type of pattern. Okay, take it as a almost that at the proper particular clock edge, first clock edge, suppose this is a clock edge 1, and at this particular clock edge the data is coming out from this Q1 pin. Okay, forget about that there can be a clock to Q delay. Forget about this F1 now. Take it as a ideal clock to Q delay. And because of that combinational circuit delay, there should the data at the D2 point, the data may be delayed by this much amount of time, but the delay can be there. This much amount of delay is tolerable. But when actually the data will sample at the next clock edge, and we will see the output at the Q2 point, the data should be stable by that point. The data should be almost stable by that point. So I have almost, you can say, this much amount of setup time window I have, you can say. This is a delay because of combinational circuit. You can say this is a comb circuit delay. And obviously this is a second clock edge, and between that there is a this is a clock time period. So I hope that I I am able to teach you that how with the timing diagram you can understand the capture flop of the sample edge. I think I'm able to teach you that when you try to sample the data at the D2 point at the capture flop, how much setup window you will get by the next clock edge when you try to sample. By the next clock edge, when you try to sample, how much setup window you will get. This is a one way to see the setup time basic definition. Another definition I can say, take it as this is a data, this is a data sequence, suppose, is coming at the D1 pin, at this D1 pin. Okay. As far as the setup time suggests that whatever this data sequence D1 may be coming at this flop 0, from that launch flop, whatever the data you are launching, by that next clock edge, the data should be properly sampled by the next capture flip flop. So, as per the definition, how we can write the data here? Think about that. So, there is a initial state I define PQ of that Q1 and Q2 of the two flop, and A, B, C, D, E as a data sequence as coming. So, as per the definition I just said, the data should be properly sampled by the next clock edge. So that P can coming as here, A is coming at this clock edge, then B is coming here and C is here, D is here. By that next clock edge, A should be there, B should be there, C should be there. So simply I try to explain that whatever the definition I just said as a sentence, same thing I said that by the next clock edge, the data should be properly sampled at the capture flop. So this is a two definition I can say. I hope that you understand. For your properly understanding purpose, I here also written that what is the late analysis or setup analysis. The same thing I am just reading. In effect of the clock fails to capture the right data due to the late arrival at the capture flop, so the logic can goes to the invalid state. So this setup time analysis also called as a zero clocking things. So to avoid that zero clocking, we should, like, it is checking whether the delay between the two flop is not, it should not be too high, and it should not be happen that in capture flop the data should not be reached too late. Data should be synchronicity last. The data synchronicity should last as much as possible. So avoid the zero clocking means actually we do the setup analysis, or we actually do the maximum analysis, or you can say it as a late analysis. So this is a basic definition for a setup time constraint I tried to explain here. In the next video, I'll come more about the mathematical expression, how you can represent the setup time with a mathematics equation. So thank you for listening this video with patience. Thank you.